Yeah. Can somebody say if you can see the presentation on the screen?
Yes.
Yes, I can see. I
Yes.
confirm.
Thank you.
Not now. Ah, yes. Yes.
Okay, perfect. So, okay. 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 So, good morning to everyone. Thanks for coming. This is an important moment for me. This is the presentation of my thesis. It's entitled Development of an Integrated Method for Formulating Strategies Concerning Energy, Climate, and Air Quality. It was developed under the supervision of Professor Alain Clapier. So, regarding the global warming, we have seen the increase in the temperatures during the last decades, and these rise in temperatures has different many effects on the climate, such as floods, droughts, and forest fires, among many others. And this rise of temperatures is linked with different activities of different sectors. Among them, we have, for example, agriculture, deforestation, or other sectors. But there is one key sector which is responsible for most of these greenhouse gas emissions, and it is the energy sector. As you can see, it's a sector that is increasing over time. And it's for this that it is important to study the assembly of the energy system. To take a look into the energy system, we can start by looking in the demanding sectors such as transport, industry, or residential. And these demanding sectors of energy will take us the energy from initially from primary resources. We can see for example, the oil, coal, and gas, which can be transformed and processed to obtain energy in different forms, such as fuels or heat, for example. And if we take a look on these resources, oil, coal, and gas, we can see these are carbonized sources. But we can alternatively get also fuels and heat from renewable resources, for example, the biomass, which can be also processed to obtain these forms of energy. But we can also use these fuels to produce electricity and as a side product, heat through cogeneration. We can also have other kind of decarbonized sources, such as nuclear energy, to produce the energy, the electricity, and we can also have renewable sources to produce directly the electricity. So here we can see the electricity is a complex system. It's not only consumed by all the sectors, but it is also produced from a diversity of primary energy sources. So it's why during my thesis, I focused mostly on the analysis of energy strategies to produce electricity. To develop these energy strategies, the process involved creating and comparing an important amount of different scenarios. But this process is complex due to many reasons. One is that there is an infinite possible number of combinations of sources and technologies to produce electricity. And there is also many criteria that can be considered regarding the different cases. During my thesis, I used two study cases. One is Cuba, and the other one is the region of the Grand Est. These two cases are different regarding the potential of renewable energy sources and also the geographical location. But in any case, we will find that the energy costs are always a critical aspect to consider. So now, to show how we can calculate the energy production cost, we can take as an example the conventional thermal power plant. And there is two aspects to produce electricity from this type of facilities. One is the number of size of the facilities, and the other one is the amount of energy needed to produce the electricity. To estimate the cost, we can do it in the form of a total annual cost, and it will depend on two terms linked with these characteristics. One is the installed capacity, and the other one is the energy produced. As a parameters, we can have the characteristics of the technologies in the system linked to the installed capacity. We have the investment cost and fixed cost, and associated with the energy production, we have the variable cost and the fuel cost to produce the energy. To produce a certain amount of energy, we should install a certain power capacity to obtain this as a product. If this capacity is fully used at 100%, we will produce an amount of energy which is equivalent to the installed power capacity. And we define the ratio between these two quantities as the energy production over the installed capacity. We can define it as the capacity factor. And in this condition, we will take the value of 1. But in reality, this doesn't happen like that. The installed capacity is not fully used, and it will produce only a fraction of the energy that it can produce in ideal conditions. As a result, we get that the capacity factor will take always a value which is lower than 1. And this is due to several reasons. One is the need of maintenance. So we need to stop the facilities to do maintenance activities. Other one is the time variation of the demand. And the other one is the availability of the resources itself. Based on that, we can identify two types of resources. One is the demand-driven resources. We call them controllable resources, and they're able to follow the demand variation over time. And another type is the resource-driven resources. These resources, we call them intermittent resources, and they have two characteristics. One is they cannot follow the variation of the demand over time, and they cannot produce energy if the primary resource is not available. It means if there is no solar radiation or wind blowing. To illustrate the interactions between these two types of resources, we developed this figure, this plot, that show the energy production of these two types of sources, the controllable sources and the intermittent sources, for different percentages of introduction of solar and wind energy into the system. We can see the trend along this driven variable, and it is that when we have a small introduction of intermittent energy sources into the system, when we have solar, sun, and wind, we will produce energy from these sources. And when we have not these resources available to produce electricity, we will need to complete the demand with this gray part that represents the controllable sources. Here, as a result, you can see with an increasing rate of intermittent energy production, we will reduce the energy production from the controllable sources progressively, and we will have also moments in which the resources are available with a sufficient amount to overproduce energy even beyond the demand, and in those cases we will have an overproduction situation. That's why in some of these scenarios of a large installation of solar and wind energy sources, we have a net overproduction of electricity. Now, in a similar way, regarding the installed capacity, we see that it is necessary to maintain the installed capacity despite the introduction of energy sources in the system. And this is because when we have moments when no solar radiation or wind are present into the system, we still need to produce electricity in an enough quantity to complete the demand and reach the peaks. So this power capacity remains necessary. And as a big result of these interactions, if we take a look on the capacity factor of the controllable sources, we see that it will decrease progressively with the introduction of solar and wind sources due to the the phenomenon I just showed you before. Now, how can we estimate the total annual cost of an scenario using this distinction between intermittent energy and controllable energy sources? We just add the cost associated to these two kinds of sources. Starting by the intermittent sources, we use the expression I just showed you before. And if you remember, we have the installed capacity and the energy production of each source for solar and wind, and the parameters depending of the technologies. But with the intermittent sources, we don't have a fuel consumption or variable cost. It will cost really the investment only, and so we can just avoid these two terms. And using the expression of the capacity factor, we can rewrite the cost of solar and wind energy as it is showed here, as we showed here. Now we will define some parameters. One first parameter is called alpha. It's the energy produced by solar and wind over the demand of one scenario, and it will represent the part of the demand that is produced from these intermittent sources. And in this share of intermittent sources, we will have a distribution between solar and wind. This parameter is called beta solar or beta wind. Like this, we can rewrite our equation of intermittent total annual costs based on these parameters. And actually, and this is useful because we will generate our alternative scenarios by varying these two parameters. Now, regarding the cost of controllable sources, if you remember, this plot is for the installed capacity of the sources in the energy mix, in the energy system. We can split the controllable installed capacity in two parts. The first part, we call them IC star for an scenario, and it represents the installed capacity needed to produce the controllable sources when there is no presence of intermittent sources in the mix. And we will have a second part of the installed capacity of controllable. We call them delta IC, and it will represent the part that should be installed to complete the intermittency due to the introduction of solar and wind to the system. In the mathematical form, if we take a look on the equation to estimate the cost of the controllable sources, we will initially sum up the cost for each technology. And for each technology, we will use the expression I just showed you before, once again. And we will introduce this concept by splitting the installed capacity in these two terms, each with its associated parameter of cost. As a result, we will get that the total annual cost of the controllable sources will have two parts, one linked to the IC star and one linked to the delta IC for each scenario. Now we will define another parameter. It's called gamma, and it represents the fraction of the energy produced of the controllable sources by one technology in the mix. Like this, we can rewrite the cost of the total annual cost star like this, using again the concept of the capacity factor. And we will propose also this parameter called phi, which is the fraction of the installed capacity of each technology into the mix. Like this, we have these two expressions to estimate the total annual cost of the controllable energy into the system, and it will correspond to the sum of these two terms. So now, this is an important part of my work. It's an important contribution because it allows us to optimize the costs. As you can see, there is an interaction between these two terms. It will represent the mix of technologies into the energy system. And with this formulation, we can use two sequential steps to optimize first this initial term by minimizing the value of the total annual cost star to fix the gamma, which will give us the energy production of each controllable technology in the mix. And in a second step, we will optimize the second term to fix the mix regarding the installed capacity of each technology. To do this, we developed a model, and the model is structured in two modules. The first module will perform an energy balance using as input data the hourly variation of the demand and the hourly intermittent energy production. It uses the residual energy, which is the difference between the energy demand and the intermittent energy production hourly, to calculate, the controllable energy sources. So when there is enough intermittent energy production to fill up the demand, let's say, we will use the intermittent energy. But when the intermittent resources are not available, the model will give us, as a result, how much energy should be produced from the controllable sources to fill up the demand. And again, we will perform this calculation for many scenarios. The scenarios will be generated by varying the alpha parameter and the beta parameter I just showed you before. Then, in a second module, we will perform the optimization of cost to define the energy mix. Here we introduce additional input data regarding the availability of the resources and the cost of each technology in the mix. The optimization of the cost will give us, as a result, the share of each technology regarding the energy production and installed power capacity. As a result, we can also, based on these characteristics of the resources, compute a set of indicators. And these indicators will be compared to a baseline scenario. We use as baseline scenario an official projection of the energy system or an official plan. So to illustrate this, this is the case of the Grandes region, the SADET plan for 2050. And the formulation we use for the indicators is a ratio between the characteristic in a generated scenario and the characteristic projected by the official plan. Here we just designed this set of indicators, the total annual cost, which is always computed by the module, and it corresponds here in this plot to the blue line. Here, similarly as before, we have different scenarios of intermittent energy introduction, and the score of each of the indicators. We have also computed the CO2 emissions, the greenhouse gas emissions, the energy imports, the use of non-renewable energy sources, and the surface land occupation to install the solar panels and the wind turbines in the region. So here you can see that the costs are quite similar to the baseline scenario, and then it starts to rise when the energy starts to be overproduced. And the other indicators, such as the greenhouse gas emissions and energy imports, are reduced when the introduction of intermittent energy into the mix. In the case of the Grandes region, the use of non-energy resources is zero, since the plan already considered there is no use of non-renewable in the 2050. The model we developed also give us as information the energy mix, the electricity mix. Here, the big plot it represents the cost of different scenarios. Each bar is one scenario, and each color represents one technology. You can see there is like two types of colors for each technology. The continuum color represents the fuel cost or variable cost, and the hashed color represents the fixed cost and mostly the investment costs of each technology. So like this, we can see the trend that the scenarios will follow when the intermittent energy is progressively introduced compared to the baseline scenario. We can see that there is three types of scenarios we identified when there is a small introduction of solar and wind energy sources into the mix, we see it is similar to the baseline scenario regarding the cost. Here we have the energy production and installed capacity, which are the two characteristics we talked about before. And we can see the scenarios with low introduction of these intermittent sources is similar to the baseline. When it starts to be more important, the introduction of these intermittent energy sources, we see that the controllable installed capacity remains necessary despite the introduction of intermittent energy production. And when we have a large share of intermittent sources, we see that we will need progressively more surface to install the infrastructure. Now, those scenarios were without energy storage. If we want to consider the storage of energy in our model, we'll take a look again on the model structure. And regarding the energy balance, we will introduce the same input data. And as output, we will include the storage of energy. So when there is an overproduction of intermittent energy, we are we are able to store this energy and then use it when there is no enough intermittent sources available to produce the electricity. And this will have effects on the controllable energy sources again. Like this, when we can also have the situation we already consume all the stored energy, and we need to call the production of controllable sources. So at this first module, we will compute these two characteristics: the storage, the energy storage, and the controllable sources, which are then feed into the second module to optimize the cost and set the energy mix. To estimate the cost of energy storage, we add a term to the total annual cost for the part of that corresponds to the energy storage. And the form of the equation is similar to the energy sources. We have two terms, one regarding the energy stored, the amount of energy stored, and a second term linked to the storage capacity in the system. The parameters also will depend of the technology. It will correspond to the variable cost and the investment and fixed cost of each technology. And it will be computed also regarding the specific characteristics of each technology. For energy storage, there are many available technologies. We have, for example, some gravitational technologies, inertial technologies that are available to be used. For our analysis, we choose only one, the cheapest one, and we got results that show us the energy storage is too expensive for two reasons. The first one is that stored energy needs a lot of capacity. We need to store a lot of energy in some scenarios. And a possible solution to that will be just to limit the storage capacity in those cases. Another reason is that the storage costs are just too high. It's too high to just invest on the storage cost. And for that, the solution will be to reduce the cost of implementing these technologies. As a result of the energy mix with energy storage, we used, as I said, the cheapest technology, and we divided by 50 times. And these are the results. We identified again three types of scenarios when we involve energy storage. The first, again, is when we have low introduction of solar and wind sources into the mix. It will be similar to the baseline. And we can see here the black line correspond to the cost of the scenarios without energy storage. This means that there is no big difference between the scenarios with storage of energy and without energy storage. In fact, we have here the scenarios that are the cheapest one between those two types of scenarios. So when we have energy storage, there is not really a big difference. We don't have a big benefit. But when we introduce a greater share of solar and wind energy sources, we improve at the same time the indicator of emissions of greenhouse gas, and we reduce the need of importing energy. And if we introduce a largest share of intermittent sources, we can see with the use of energy storage, we can get into a situation when we don't need controllable sources, but it will need anyway to overproduce energy with the solar and wind sources. We also perform an analysis of the robustness of our results, and we found that the cost of solar and wind are decreasing, and they are actually now lower than other technologies costs. So the trends we have seen in our results will be maintained if the trends of the cost evolution remains the same. And regarding the energy demand, there is two sources of uncertainty. One is the average demand, because this the value of the demand projected in 2050, and there is also an uncertainty regarding the time scale for the variation of the demand only. We have performed an analysis of the results using two projections. The official projection of the STRADEP scenario for 2050, which considered that the energy demand will increase from 44 terawatt hour in 2021 to 39 terawatt hour in 2050, and a less conservative scenario that consider an increase in the electricity demand going up to 74 terawatt hour in 2050. So as a result, we see that the cost will increase since we need to fill up a bigger demand. And in fact, we will need to introduce additional sources to complete the demand. Here in the case of the region, we introduced the nuclear energy. And as a first regard, we see that the baseline is the most expensive scenario, and is due to the cost of introduction of nuclear energy into the system. So now, if we see the cost of the optimum, let's say the less costly scenario, which is around 70% of solar and wind in the mix, we see it can be very different, going from 2,000 to the double if we consider the maximum increase of the demand. And regarding the use of land surface to install the solar panels and wind turbines, it will also increase from 3% of the region's surface to 6%, which is the double. Now, if we pass to the conclusions, we have developed a method to design and evaluate many scenarios, trends, by calculating at the same time a set of different associated scenarios, indicators, sorry. The method was applied in two study cases, Cuba and the Grandes region, and we found that there is an economically competitive replacement of the solar and wind sources to the controllable sources when we don't have energy storage. And the full substitution of the controllable sources by solar and wind is not possible if we don't use energy storage. But anyway, to install a great capacity of intermittent sources will be necessary to accomplish this. The scenarios with energy storage are more expensive than the scenarios without energy storage, and there is an competition between the cost of controllable sources and energy storage to overcome, let's say, the introduction of storage into the energy scenarios. Based on the analysis performed for the sensitivity of the demand, we can say that the tendencies of the scenarios we found as a result are robust, and also the trends of the indicators computed. We also have some perspectives for the future work to be done. One is regarding the alternatives of storage management. This is the different ways we can use the energy which is stored to be deployed to fill the demand. The optimal size of the studied region. If we think in the size of the region we are studying, and if we imagine the size of the region to be small, we will need to import the resources to produce the local energy demand. So that means there is a restriction. And if we consider a too big region, another cost, such as the cost of transportation, will become important. And in that case, the model has to be adapted. We can also think that in between these two extremes, we will have an optimum, and it has the merit to be studied. Another aspect is to study the electricity pricing policies, because as a result of introduction of these sources, intermittent sources, we will have moments of overproduction, and due to the law of offer and demand, we will have moments of low prices, even negative prices. And regarding the development of the tool, the model is still in a back-end stage. So the development of a graphical user interface will be needed in future developments. Some thesis products arise from this research. We have published one article in an international journal. We have already submitted one second article, and we presented these results in 5 oral presentations, international events, and some preliminary results were published in one book chapter. I would like to thank also the institutions that made this work possible, and thank you all for your attention.